Hello everyone, my name is Soham Banerjee, and today I'll be giving a presentation on SMT-based modeling and verification of spiking neural networks. This is a joint work done in collaboration by Indian Statistical Institute, Kolkata and Ericsson Research, Bangalore. So let me begin. A spiking neural network is a special type of neural network whose structure and operation closely mimics that of a human brain. Where traditional neural networks would use real values for its computing, a spiking neural network would use a sequence of signals instead. These neural networks are very useful for neuromorphic computing, that is computation in the context of various audiovisual stimuli. Spiking neural networks have very low power requirement in comparison to traditional neural networks and can run on unique hardware. Where traditional processors require a large amount of power, neuromorphic processors for SNNs have very high throughput for a fraction of the power required. There is also a temporal component to its execution, where traditional neural networks would supply real valued vectors to the models one at a time. Spiking neural networks provides its inputs in the form of spike trains, which is a sequence of signals spanning over a fixed amount of time. In the figure here, the sharp vertical lines that you see here correspond to the spikes being propagated. There are many different types of neurons for SNN, out of which the most common one is leaky integrate and fire neuron, which is the focus of today's work. Let me give you a brief example of an SNN. So let us consider this SNN here, which is comprised of 6 neurons and weighted edges connecting each other. Now, when a neuron receives an input signal, it starts building up a potential until a specific threshold is met. Once the specific threshold is met, all the stored potential is lost and the neuron will send out an output signal. This means that a neuron is inactive until the threshold is met. So in this context, let us consider two input spike trains, gamma 0 and gamma 1, corresponding to N0 and N1. And let us say that the neuron threshold for all the neurons is 1. Here, we can see that at time step t is equal to 1, both N0 and N1 give an input spike. So if you look at N3, upon receiving a spike from N0 and N1, will start building the potential equal to 0.5 minus 0.1. Adding these together, the stored potential becomes 0.4. So since 0.4 is less than the threshold 1, N3 will not send out an output spike. This cycle continues for each time step. And as you can see at time step 4, both N3 and N4 have crossed their potentials. And upon crossing their potentials, they have both sent out an output spike to N5, where N5 has stored the potential of 2, corresponding to the 2 synapses which have sent in an input signal. So all three N3, N4, and N5 will spike since they have at time step 4, since they have crossed their threshold. Now, let's look at LIFR neurons. Now, LIFR neurons is a 7-tuple where psi corresponds to the input set of input synapses. Weight or W is the weight assigned to each of these input synapses. Y is the output function of the neuron, which is basically the activation function of the neuron. Theta is the threshold of the neuron, which has to be met before it can be fired. Tau, refractory period, is the amount of time a neuron has to wait after sending out a spike before it can start building up potential again. Lambda is a leak factor, which is a leak that occurs over time. Leak in the potential that occurs over time. And P is the stored potential function, which is initialized to 0. The potential of a neuron at time step t is given as the previous potential at time step t minus 1 after applying some loss, along with the accumulated potential at time step t. This is essentially the weights added together corresponding to the input signals received at time step t. If the potential at time step t minus 1 was less than theta. If the potential at time step t minus 1 had crossed theta, then at t minus 1, the neuron would have sent out an output spike, which would then mean that we do not need to consider the previous potential for this time step. So the potential at time step t in this condition would just be the accumulated potential. Finally, the output neuron function is quite straightforward, where the output neuron function returns 1 if the potential is greater than the threshold and 0 otherwise. So now let us look at some related work. There are many SMT-based frameworks for modeling and verification of traditional neural networks like ReLUplex. These frameworks all use SMT encodings to encode the neural networks and use those encodings for formal verification. Now, due to significant differences between SNNs and traditional neural networks, these frameworks cannot be used for spiking neural networks. So we need to come up with a framework that can model SNNs along with their structure and operational properties. Then we also need to use this model in order to formally verify spiking neural networks. So in this work, what we have done is that we have proposed a SMT-based encoding to model spiking neural networks. We have shown how the encoding of spiking neural networks can be used in the context of formal verification, specifically for verification of specific properties and for verification of adversarial robustness. Now, let us start with the SMT encoding. So the SMT encoding is a linear real arithmetic formula corresponding to the neural network. This LRA formula of the neural network is a conjunction of the LRA formulas corresponding to each neuron. The LRA for each neuron is made up of 5 formulas for each time step of execution and 1 formula for the first time step. The 1 formula corresponds to the initialization condition, where at time step 0, neuron I, for neuron I at time step 0, the potential should be initialized to 0. The second property or the second formula is that at time step t for neuron I, the accumulated potential is equal to the weighted sum of all the inputs received. So here, for all inputs j, if there is an input spike received from j, then xjt would be 1 and the associated weight would be added to the accumulated potential at time step t. Otherwise, xjt would be 0 and no weight would be added to the accumulated potential. Now, using these two, let's move on to the third one, which says that a neuron spikes if and only if the stored potential crosses its threshold. What this means is that the accumulated potential SIT along with the previous potential PIT minus 1, after applying some loss, let us call this total potential. If the total potential is greater than the threshold, then there should be an output spike. So XIT should be equal to 1. The counter positive of this statement would be that if the total potential is less than the threshold, then the neuron should not spike or should give an output of 0. Now, the next property is pertaining to the potential of the neuron, where if the total potential of the neuron crosses the threshold, then we can reset the potential back to 0. So in this context, if the total potential crosses the threshold, we set the potential at time step t is equal to 0. So in the next time step, when PIT minus 1 is called, it would be actually be equal to 0. And the counter example of this one would be the total potential of the neuron. If it is less than the threshold, then the potential at that time step will be equal to the total potential. So we essentially store the potential for the next time step. So when we go to the next time step, we will have this sum as the previous potential that we'll apply loss on. So combining all of these properties, these 5 formulas for each neuron and each time step, we get the following encoding for the entire network, where the entire network is essentially for all neurons, the initialization condition, and for each time step, each neuron, we have the next 5 properties that we discussed about. So this giant conjunction is the entire encoding of the neural network. Now that we have successfully encoded the neural network, now we can move on to verification of spiking neural networks. So verification of a spiking neural network is a problem where, given a spiking neural network N, an input property P, and an output property Q, we need to decide if there exists a gamma for which the input property is satisfied, the network generates an output eta, and the output property is not satisfied. The encoding of P and Q can be done using LRA, similar to that of the neural network. And then the entire formula, which is now in an LRA form, can be given to a SAT solver who can then check the satisfiability of this formula. In the context of this work, the SAT solver we have used is Z3, and this to simulate SNNs on traditional hardware, we have used SNN torch. Now let us look at a specific example of the verification problem, that being adversarial robustness. Now adversarial robustness for a spiking neural network N is the robustness against some input noise. That means that upon adding some input noise to the spikes, we still get the correct output or the same output from the neural network. Where for a classification problem, the same label is selected. The neuron corresponding to the correct label will have the maximum number of spikes. Now, what is this noise? We call it delta perturbation. Now, delta perturbation of gamma of gamma naught is a spike train gamma, where the number of positions at which the spike train is different from gamma naught is at max delta. So it is a bounded difference. So if the value of gamma is 10, that means that our perturbation can have up to at max 10 positions at which it is different from the base gamma naught. Now, how we do this in the context of verification is as follows. We encode the input property P on gamma as follows, where we take the XOR for the entire spike train. We take XOR with the corresponding gamma naught, where the difference in input would yield a 1 and similar inputs would yield 0. So we take a sum of those differences, and if the total count of the positions at which the spike train is different has to be at max delta. So this is the condition for the input encoding, and for the output encoding, we have that the label predicted, that being y0, should have the maximum number of spikes even after applying the input noise. So basically we say that it should predict the correct label. Now, what we can do is the encoding of input property along with the negation of the encoding of the output property and the encoding of the neural network that we had, we can create a large conjunction of an LRA and then give it to a solver. If the solver returns SAT, we can say that there exists a delta perturbation of gamma naught for which the network has generated an incorrect output, which means the network is not adversarially robust against delta perturbations. If the solver returns unsat, which means there is no value for which, no perturbation of gamma naught for which the network fails to give the correct output, which means that our network is adversarially robust against all delta perturbations of gamma naught. Now, in this work, for the results section, we have considered SNNs trained on the IRIS flower dataset, which is a dataset with 4 input features and 3 output classes, as well as MNIST handwritten digits dataset, which is a dataset made up of 28 by 28 pixel images of handwritten digits and labels corresponding to each digit from 0 to 9. So for the SNN IRIS dataset, where our network has an input neuron, we have 4 input neurons and 3 output neurons, and we test the adversarial robustness for 5 different values of gamma naught. We see that with increasing value of delta, the number of robust instances goes down. So for lower values of delta, all the inputs are robust, the network is robust, but for higher values of delta, we slowly start to see that the number of robust instances goes down. We can also notice that since the increase of value of delta causes an increase of the number of perturbations, we can also notice that the time taken for the SAT solver also greatly increases and even leads to some timeouts towards the end. Another result that we have for the context of MNIST dataset is that here, considering an MNIST network with 784 input neurons, which is the 28 times 28 input features, and the 10 output neurons corresponding to each digit 0 to 9, we see that upon increasing the number of neurons, the accuracy of the model goes up, but the total time taken for the solver to let us know whether the network is adversarially robust or not, or to return SAT or unsat, also increases greatly. This table is generated just for delta is equal to 1. Immediately switching from delta is equal to 1 to delta is equal to 2 causes an exponential size growth and causes a lot of timeouts. So to conclude, we have seen the introduction to spiking neural networks. We have seen the leaky integrate and fire neuron architecture. We have seen LRA encodings of SNNs. Then we have seen verification and adversarial robustness of SNNs using the proposed frameworks. For our future work, we want to develop the framework further so that it can generate results in reasonable time. and can have better scalability than the current framework. We also want to consider using different encoding techniques apart from LRAs, like mixed integer linear programming. That might be the key to the optimization we are looking for. And we would also like to expand our encoding to cover a wider range of SNN neurons, where in this work we have considered leaky, integrate, and fire neuron. We can expand the work to cover additional neuron types and different spike encodings. Thank you for attending my presentation. If you have any questions and queries, feel free to write to me.